Welcome back to Daily Dose of Space. Gravity is the oldest force humanity has tried to understand. It explains falling apples, planetary orbits, the motion of galaxies, and the expansion of the universe. It holds stars together and shapes the largest structures in existence. And yet, when scientists apply gravity to the universe as a whole, something does not fully add up. Dark matter had to be added to explain how galaxies rotate. Dark energy had to be introduced to explain why expansion accelerates. Now, the expansion rate itself refuses to agree depending on how it is measured. At some point, a quiet question begins to surface. What if gravity, as we understand it, is incomplete? The success that built confidence. Einstein's general theory of relativity has passed every experimental test thrown at it. It correctly predicts the bending of light around massive objects, the behavior of GPS satellites, the existence of gravitational waves, and the motion of planets with astonishing precision. On small and medium scales, gravity works beautifully. It is elegant, mathematically consistent, and experimentally confirmed. This success created confidence. If gravity explains everything from falling objects to black holes, then surely it governs the entire universe reliably. But cosmology deals with scales that Einstein himself never observed directly. Billions of light years, structures larger than anything imaginable in daily life. And on those scales, strange things begin to happen. The dark matter problem. The first serious hint that gravity might not tell the whole story came from galaxy rotation curves. When astronomers measured how fast stars orbit the centers of galaxies, they found something unexpected. Stars far from the center were moving much faster than gravity from visible matter alone could explain. According to Newtonian intuition, outer stars should orbit more slowly, just as outer planets in our solar system move more slowly than inner ones. Instead, galaxies behaved as if they were embedded in massive halos of invisible matter. The solution proposed was dark matter, an unseen form of mass that interacts gravitationally, but not with light. Dark matter fits many observations remarkably well. It explains galaxy clusters, large-scale structure formation, and patterns in the cosmic microwave background. Yet, it has never been directly detected. Some physicists began to wonder whether dark matter is truly a new type of particle, or whether it reflects a modification needed in our theory of gravity. The birth of alternative gravity. In the 1980s, alternative theories emerged. One of the most well-known is modified Newtonian dynamics, often called MMOND. Instead of adding unseen matter, MMOND adjusts the laws of gravity at extremely low accelerations, precisely the regime where galaxy rotation curves become puzzling. Surprisingly, MMOND can reproduce many galaxy rotation observations with impressive accuracy. It does so without invoking dark matter particles. However, MOND struggles to explain cosmological observations on larger scales, such as galaxy clusters and the detailed structure of the cosmic microwave background. Each success in one area seems to create tension in another. This back and forth has kept the debate alive for decades. Gravity on cosmic scales. General relativity assumes that gravity behaves the same everywhere and at every scale. But what if that assumption fails over billions of light years? Some modern theories propose subtle modifications to Einstein's equations that only become noticeable at vast cosmic distances. These modifications could potentially explain accelerated expansion without invoking dark energy as a separate component. In such models, what we interpret as dark energy might actually be a sign that gravity behaves differently in extremely low-density environments. Testing these ideas is extraordinarily difficult. The effects are subtle, and require precise mapping of galaxy distributions and cosmic expansion over enormous volumes of space. Gravitational waves and new clues. The detection of gravitational waves opened a new window into gravity itself. These ripples in space-time, produced by merging black holes and neutron stars, allow scientists to test relativity in extreme conditions. So far, the results are consistent with Einstein's predictions, but they also provide constraints on alternative gravity models. Some theories have already been ruled out because gravitational wave observations did not match their predictions. This process narrows the possibilities. If gravity is incomplete, the deviation must be subtle enough to avoid contradicting the growing body of precise data. The risk of adding too much. There is a philosophical tension at the heart of this discussion. Dark matter and dark energy together make up about 95% of the universe's total content. Only a small fraction consists of ordinary matter. One way to interpret this is that most of the universe is composed of invisible components that we have not yet directly detected. Another interpretation is that our equations may be missing something fundamental. Historically, physics has faced similar crossroads. Sometimes the answer was new particles. Sometimes it was a new theory. The challenge is distinguishing between the two. Why gravity is so hard to replace. Gravity is deeply woven into the structure of modern physics. General relativity is not just an equation, it is a geometric description of space-time itself. Modifying it risks breaking other successful predictions. Any new theory must reproduce all existing conformations of relativity while also solving the dark matter, dark energy, and expansion rate problems. That is an extraordinarily high bar. This is why most cosmologists still favor dark matter and dark energy over modifying gravity. The standard model works extremely well in many domains, but the tension remains. A universe that might be hinting. The Hubble tension, the nature of dark matter, the mystery of dark energy. These are not isolated puzzles. They may be connected pieces of a larger issue. If gravity behaves slightly differently under certain conditions, it could subtly alter expansion history, structure formation, and galaxy dynamics simultaneously. The possibility is not that Einstein was wrong, but that his theory may be incomplete when applied to the full cosmic scale. Physics has expanded before. Newton was not discarded. His laws were shown to be approximations within a broader framework. Gravity might be awaiting a similar expansion. Living with uncertainty. For now, gravity remains one of the most successful theories in science. It guides spacecraft, predicts black hole mergers, and explains planetary motion flawlessly. Yet, when we zoom out to the scale of the entire universe, we encounter components that cannot be directly observed and numbers that refuse to align perfectly. Whether the solution lies in undiscovered particles or a deeper revision of gravity itself, one thing is clear. The universe still has leverage over our certainty, and gravity, the force we thought we understood best, may still hold surprises on the largest scales imaginable.